Hi, and welcome to this lecture on NumPy. Now, what exactly is NumPy? NumPy, which stands for Numerical Python, is a core library for scientific computing in Python. So it's a module with a lot of fancy functions for working with stuff like matrices, for example, or even multidimensional array objects such as tensors, right? So that means that you have a lot of functions open for you and that have a lot of functionality within them and optimized in a way that they work really fast to help people like us in scientific fields to perform functions that we wouldn't have to write code from scratch. Now, an example of this would be, let's say, I want to compute a determinant of a matrix, or I would like to generate some random numbers according to some certain distribution, such as binomial distribution or Gaussian distribution or so on. Without you having write the code down and from scratch and, having to save the code and worrying about, I don't know, maybe losing the code. Well, you have this library called NumPy, which helps you basically, which saves a lot of time for you. You have all those functions ready for you to be used. So if you're in machine learning or in statistics or even maybe in economics or finance or whatsoever field that requires numerical computations, this is the best module for you, I would say. Now, if you already worked with MATLAB, you will find that NumPy is really close in essence. But NumPy is very lightweight. You don't need to install MATLAB, which is something that is paid. MATLAB is paid, it's not free. So, on the other hand, NumPy is open source, which means you can contribute to this community. You could also, let's say, if you would like to suggest some modifications, you can go ahead to GitHub and find the contributors. You can ask questions about it and so on. All these cool stuff. So without further ado, let's get started. So I'm going to use something called Jupyter Notebook. Now you can use whatsoever IDE, such as Visual Studio Code or IntelliJ or whatever editor you'd like. I am going to use Jupyter, which I could install as such, pip install Jupyter as such on my terminal. If you're on a Mac, this is a terminal. And if you're on Windows, you have to open command prompt and type in the same command. Now, if you're using Python 3-, which is 2.x, right? You're going to have to run this command. If you're using Python 3+, you have to use pip3, install Jupyter. You run it, and it might take some time. I already have it, as you can see. Requirement already satisfied. Now, if you don't have it, it depends on your internet connection because it's downloading the module or package for you, right? So if you have a high-speed internet, this will take less time, okay? Now, once you're done with that, I'd want you to go to any directory that you prefer. I'm going to go to my desktop. And then I'm going to navigate to, I created an empty testing, okay? This folder is empty. And all I have to do is type in Jupyter as such and notebook. Now Jupyter is not, it's written in the wrong way. So no, this is still not correct. So let me just use tab as auto-completion and Jupyter notebook as such. And now you see why I had my Google Chrome right here. You see, I could directly work on Google Chrome, for instance, or any other browser. So this I won't be needing for the moment. Terminal, the terminal you see here, you shouldn't close it, okay? If you close it, you're going to see an error. This will no longer respond to you. Okay? For the moment, I'm just going to minimize terminal. Do not close it. I repeat, do not close it, or else all your work, now they will be saved, but you will not be able to run code or do some sort of interaction with Python. Okay? So I just minimized my terminal, and now let's go ahead and create a new notebook. So new, I'm going to work with Python 3, and this is my notebook. Okay? As you can see here, untitled is the name of the notebook. I'll call it Learning NumPy or NumPy as such, with an underscore here, and rename. So in your folder, you should be able to see this file .ipynb, which stands for Python Notebook. Okay? So now here we have something like a command prompt. Like you can just type in some commands as such, 2 + 2, shift enter, and you get the corresponding output, which is 4. Now we need NumPy in our programming stuff. We need to import NumPy, right? Now, since I have it on my computer, I do not need to install it. Now, if you do not have it, you have to follow the following steps. Now, here I have another instance of my terminal running. All you have to do is shell, new Windows, basic, or anything, right? And a new Windows will pop out for you. Do not use the old Windows that we opened for the Jupyter notebook, because as we said, we shouldn't close the other one, and we cannot enter commands in it because it's already executing some code to keep Jupyter running on the browser. Okay, so we have to run a new browser, a new instance of the terminal as such, and go ahead and type in pip3 install NumPy. Now, as I mentioned before, since I have NumPy, it will not download. Now, NumPy is a dense module, so you'll have to leave it some amount of time. Okay. Okay, so back here on the Jupyter notebook, and let's start with arrays. A NumPy array. So a NumPy array is a grid of values. Let me just type in. Let me just organize some stuff right here. I'll try to put some. So right here, you've got options for your cell. Now this is called a cell. It's snippets of code. So you have some code that are somehow related to each other. It's you who decides how many cells you want, for your own, for the sake of organization, nothing more, nothing less. So I could set it to Markdown, and the cool thing here is that I could go ahead and type in some text, which is not code. So let me write in over here. I will import NumPy and shift enter. As you can see, it's formatted as text, as normal text. Now you can also go ahead, if you know LaTeX or MathJax, you can also go ahead and type in some equations, which is super cool as such. So let f of x equals to x squared plus e to the power x plus, I don't know, a fraction, right? 2/3 square root of x. Hit shift and tab, and voila, you've got LaTeX embedded in your Jupyter notebook. This is amazing. So let's say you have a big document where you have some code that does some mathematical stuff, you could just type in the mathematical stuff right on top of the code. This is really helpful. So let me just remove this because this lecture is not about LaTeX. So over here, I will import NumPy. Now, I just imported NumPy, Shift Enter, and we have it ready to be used. So all I have to do is NumPy dot tab, and here's all the functions within NumPy. Okay. Now the word NumPy consists of 5, characters. So some people might find that really a lot. So that's why you see as np, which is a nickname or an alias to NumPy. So instead of having to type np.dot something to refer to a certain function within NumPy, all I have to do is np.dot instead. Okay. So let's try first of all to create a NumPy array. So how do we do that? A NumPy array is simply done as follows. So np.array, or if you forgot the command array, all you have to do is, ar and tab. You see all those are functions for you to use. So there you go, NumPy array, enter, and it takes a list as argument. So a list is nothing other than a list of values, a container of values. So 1, 2, 3, 4, 5. This will be a NumPy array. Now I can print it as such, and this is different from a list. This is of type NumPy array. So the type is NumPy.end array, which means that this is compatible with the NumPy functions. So as you will see, which is normal, NumPy, most or all NumPy functions take as arguments NumPy arrays, of course, because to perform some functionalities with some matrices, those matrices should be of type NumPy.end array, right? Okay, so this is how you create a NumPy array. Now, a NumPy array is a grid of values, all of the same type, and is indexed by a tuple of non-negative integers. Now, this is my NumPy array A. How would I extract some values? So let me go right here and let me just, you could also switch the cells if you want. Now let me go here and type in a Markdown, which is indexing elements in my NumPy array. Now how do I do that? All I have to do is, let's say A0 is the first element, it's 1. You can also go up here and change the values. So let's say you're not satisfied with 1, you would like to change it to 10, 20, 30, 40, 50. Make sure you hit Shift Enter, and again Shift Enter, so that it takes effect, and here Shift Enter. Okay? Let's say I only hit Shift Enter here, but not here. Will it take effect? Well, of course, because this is just printing. So in order to see it as an output, you have to print it here. Okay? So the first element is 100. The second element is 20, and so on. Let's say you're interested in elements from first to the second element. So 0 till 2, and there you have it, 120. So how this thing is read is from 0 till 2 without including 2. So 0 till and excluding 2. Okay? Say you want from 2 till 3, so excluding 4, there you have it, 0, 1, 2, 3. Okay? So this is how you would index a NumPy array. Now let's say you're interested in, the dimensions of your array. Say at some point of the code you'd like to extract the dimensions, or the array is given as an input to your function, and of course you would like the dimensions for further processing. maybe to loop over the matrix. I don't know, depends on the application. So all you have to do is a.shape. Let me type in here what I'm going to do. So retrieving or reading the dimensions of your array, right? So how do you do that? As simple as that, a.shape. And as you can see, it's 5, comma, nothing. So a.shape 0 is 5, and a.shape 1 is an error because it's a one-dimensional array. Okay? On the other hand, if you want to create a matrix, it's as simple as we did. So uppercase A is np.array, and you would have to cast a list to an array, but this time it's a list of a list. So what you see right now is a list which is going to be in my first row. This list is going to be in my second row. The following is in my third row, right? And let's print it. See, there you have it. 1, 2, 3, 4 is in my first row, and so on. Let's say I want to add one more row to make it square. 1,000, 2,000, 3,000, and 4,000. Good. There you have it. Okay. Now this is an array, and I would like to take. This is a matrix, a two-dimensional array, and I would like to find the dimensions. It's 4 by 4. So the number of rows is the first element, and the number of columns is the second element. Okay? So how would you index a matrix? All you have to do is, let's say you're interested in the first row. So remember, the first argument is the row index, and the second element is the column index. So what would A23 return? So 2, remember that we count from 0. 0, 1, 2, we are at the third row. So 2 means third row, and 3 means the last column. So I should be able to retrieve 400 as such. Now let's say you want a submatrix. So right here, extracting a submatrix, right? So how would I do that? It's also as simple as indexing. So let's say you're interested in this submatrix right here. 20, 30, 40, and 200, 300, 400, right? So how do we do that? So this matrix, 20, 30, 40, 200, 300, 400, starts at row 2 and ends at row 3, right? So how do I do that? Row 2 till 3 is 1, 3. So how do I make sure? Shift, enter, print. This is all the second and third rows, but I'm just interested in, starting from the second column. So I also have to index the columns as such. 1 till, if I put 3, it's not going to work because excluding. So I have to mention 4 as such. And if I don't say anything, like 1 colon as such, Python automatically understands that it will stop at the end of the matrix, okay? So let's say you're interested in extracting the second till the last column. All you have to do is what I just did. 1 till nothing, okay? Which means till the end of the matrix. Good. Now let's say you would like to modify some elements. Modify elements in an array or matrix. Markdown because this is text, right? Now all you have to do is A. So what is A right now at this moment? It's this. Let's say you don't want a 200 here, you want a, I don't know, a number of your choice. So how do we index 200? It's sitting at the third row, second column. So that being said, it's 2, 1. And let's change it to another number. Let's say 1/3 as such. Enter A, print. It's 0. Why is that? Now remember, we have right here integers. We gave it integer values. We gave this array integer values. Now if I go back here and I just say 1.0 and run, you can see that all the elements right here are now floats. Now, I have previous lectures on Python. This is a Python lecture. It's no longer a NumPy lecture. Okay, so I do the distinction. This is automatically casted as a float. This double list, or I would say a matrix list or a two-dimensional list, is now seen as a float list, and therefore all the elements are floats. If I go back down here, I could be able to see that this element right now is 0.3333 or 1/3, right? So now all your matrix is a float. Be careful to those mistakes, because I've seen a lot of students do such mistakes. Okay? So if you're working with floats, you have to initialize your matrix as a float, or at least one element as a float. Okay? Now, this is how you modify elements. You could also create some default matrices, such as the 0 matrix, the 1s matrix, the identity matrix, and so on. How do you do that? It's as simple as this. So let me just do a markdown, creating special matrices. And let's say you want the identity matrix first of all. So it's np.dot. It's the same as MATLAB. MATLAB has the same command I. So you want an identity of size 2. There you have it. Size 3. There you go. Size 10 is this big. Okay? As you can see, you have 1s on the diagonal elements and 0s in the off diagonal elements, which is an identity matrix, right? Now let's say you want a matrix of all 0s. Of course, you can create a matrix of all 1s and set the diagonals to 0, or just do, 0 times I. There you have it, right? But let's not do that. Let's do it the correct way. So it's np.dot zeros of whatever dimension you want. So 5 is understood as a, as a row. You have to mention 5 by 5 if you want it to be. So yeah, so it should be a tuple. Sorry about that. I'm missing parentheses. And there you go. Make sure that the dimensions in the np.0 are inputted as a tuple. Okay, so as such. So if I did this, I would have an error, because the input should be a tuple. Data type is not understood. The input should be an error, a tuple. Okay? So let's see what happens if I add one more argument. This is a 3-dimensional matrix. Tensors, you talk about tensors. A 4-dimensional, and so on. Okay? So let's limit ourselves to 2 dimensions. There we have it. This is the 0s matrix. This is the identity matrix up here. Now, what about the 1s matrix? The matrix filled with 1s, right? So np.1s. And then the dimensions, like 0s. So 3 by 4, let's say. There you have it. 3 rows, 4 columns. Let's give it some other inputs. 6 by 4, 6, 4, right? So this is the 1s matrix. We've also got other matrices. Let's say you want a constant matrix, like say C is np.full. So let's say you come across a function that you have never, heard about it. In case you're using, or if you're using Jupyter Notebook, you can know more about this function by simply holding Shift and pressing Tab as such. It will give you a description of your function. So as you can see here, np.full, the first argument is shape, which means the dimensions of your matrix, right, or your array. And the second argument is fill_value, which means the value you would like to replicate or fill within your matrix. Now, when you come across, arguments that have an equal or have an assigned value, like dtype, which is none, and order is, C, it's okay. You don't have to understand what that means. It means those are optional. It means it's okay not to input them. But it's not okay if you don't input this or this. Is that understood? Now, this is the signature or the prototype of your method, np.full. Now, what does it do? It returns a new array or matrix of given shape and type filled with fill value. So let's give it a try. So the first one, remember, was shape. So let's say I want a 4x5 matrix, and the second argument was fill_value. So let's say I would like to repeat 10. Enter. And there you have it. It's a 4x5 matrix with values as 10. Now, of course, you can do this with 10 dot 1s, 4, 5, right? Oh, what is the mistake? Oh, so I keep forgetting that. It's np.ones. So run, and you have the same, output. But why should I generate a matrix and then, do a multiplication? It requires double the amount of time. Why not create the matrix automatically with tens, right? So let's say this takes amount of time, 4 times 5, 20 operations. This will take 40 operations, no? Because you first created a 4x5 matrix, and then you did a multiplication with all the elements. So that's where np.full comes in, okay? And let's say you're interested in a random matrix. You want a matrix, for, for your statistics homework, or you're doing some sort of experiments, you're working with some sort of data, and you'd like to generate some random stuff, maybe for, if you're working in signal processing or communications, you want to generate some noise and add it to your signal. In case you're working with finance and with some models for, stock estimation and stuff, you would like to shock your model, you would add some, random behavior. You would add randomness to your model to reduce the risk, or, the portfolio. Depends. Okay? So how do you do that in Python, in NumPy in particular? So my random matrix is, let's say it's X, and to do that, it's np.dot. You've got a sub-module which is random. So this is dedicated for all random behaviors, random matrices, random distributions. You'd have to go to this sub-module or library, and hitting tab, you'd see all the amazing stuff, or a lot of distributions and functions that help you perform some random operations. Okay, so in case I want a random matrix, it's random.random. And then I would specify the dimensions. Let's say I want it to be 2 by 2, and then I print it. And there you have it. And by the way, I could do this. I could hit enter here and keep typing code, okay? It's the same thing. So x as such, and there you have it. Let's do it again. We have the other realizations. And as you can see, my random numbers never go below 0 and they never go above 1, which means that this should be, I'm giving it a guess right now, but this should be a uniform distribution. So random sample takes as there you have it. We can also pass it nothing and it will return a random number. Okay, this is what it means when we see, as we said before, an assigned input. So in case you do not input, it will generate a matrix of size 1 by 1 or a number. So it returns random floats in the half open interval 0, 1, which means it's a uniform distribution, right? And to make sure, let's generate a large number, a large amount of numbers, which is 10,000, and let's say I'll compute the mean, which is the average. How do I do that? Now there's functionality for that. So np.random dot, is it mean? No, I think it's np.mean. Yeah, x. There you have it. It's close to 0.5. Now this is not enough. Let's compute the standard deviation, STD of x. Now what is an STD of a uniform distribution? It's, let's do some math here. So it is the variance of x is, what is it? Is it also p? Is it 1 minus p? I think I'll go for p. Yeah, I think I'll go for p. No, but what am I talking about? This is it's not p. Ex squared minus ex all square as such, right? And to compute we should remember that this is a continuous random variable, it's not discrete, so we should be able to perform the integration from 0 to 1 of x squared, and it's an open interval on AB, so it's a 1 over 1, right? dx, this is the first part right here. I don't have a limit. Oh, so this version of LaTeX doesn't take limits. Okay, so we have this integral for the first part, and the other one is the square of the means, which is how much? Just said that the mean is 0.5, so the square of that would be 0.25. And the integration of this would be 1 over 3 minus fraction 1 over 4, which is a 1 over 12, right? So the variance. Now, since this is the variance, then what is the standard deviation? It's the square root of the variance. So if I go ahead and type in STD of x, I'll see a number, and then I'll have to square that number. So times 2, or the power 2 is square, and what is 1 over 12? It's really close, right? So it is most probably a uniform distribution, okay? So this is the true variance, and this is the estimated variance from this. Where is it? Where is it? Where did you go? Where is it? Should be here. No. Oh, come on. Print x. Okay. Of this array. Okay. So those are some special type of matrices, except the last one possibly because it's a random matrix, but we just pass it right here. Okay. Now we talked about how to generate matrices, how to index matrices, how to create matrices of specific types, how to retrieve the dimensions of matrices. Now let's talk more about data types. So this passed a while before when we were creating matrices up here, and I had a 1.0, right? So that all my matrix is now float, of type float. And if I didn't have that, my matrix will be by default integers, all consisting of integers. Now, a question is, how do I find if a matrix is a, an integer or a float or whatever? Well, all I have to do, if I'm using normal variables which have nothing to do with Python, 0.1 and y is 1 and z is a string, let's say, NumPy. So the way I find the type of those elements is just by hitting type x, which is a float, right? Type y, which is an int, and type z, which should be a string, right? Now the way you do that with NumPy is different, because if I have A, which is my array, or uppercase A, which is this matrix, right? If I type in type of A, it's not informative, right? It's just a np.nd array. It doesn't tell me much. It doesn't tell me whether my entries are integers or floats. Let me just change that to floats, and just to show you that it doesn't do much. So run this again, and there you have it. Now, what is the correct way of doing that? The correct way is using a.dtype. So this is a right here. This is a function within NumPy, right? And as you can see, it's here. It's within NumPy. Okay, it doesn't tell me much, but really, all this does is tell me what my matrix consists of. So at this point, A is all floats, and it tells me your A is all floats with 64 bits. Okay, now let's change it back to integers, i.e., let's move this 0.0, going back down, right here, and let's check the D type, which is an int right now. Okay? So this is how you would check for the data type of your matrix. Now next up, we're going to talk about some mathematical operations, how to perform matrix addition, subtraction, inverses, and all those cool stuff that you know about matrices. Okay? So let's get started with matrix operations. I've cleared out everything so that we can start from scratch. So in case you're still on the same Jupyter notebook, you don't have to run import again. So let's start talking about matrix operations, and in particular matrix addition. Okay, so how do we perform matrix addition in NumPy? Well, first let's declare two matrices. I'll set them to 3 by 3. This is my A, and my B is also 3 by 3. Okay, so run to make sure all is good. Let's say you want to visualize them. You have them over there. So first of all, matrix addition. How do we perform it? You've got two ways. So you've got the fast way, which is this, A plus B. And in case you want to store it in another matrix, it's as follows. C is A plus B. There you have it. And the second way is using NumPy's addition function, np.add. So the first two parameters are the matrices you would want to add, right? So if you execute the method as such, you're going to get the same outcome as C. But let's say you would like to cast it to another type. Let's say you're not satisfied with an int output. You don't want the outputs to be integers. You want, let's say, floats. So dtype, you would pass a third parameter as such. Dtype is np.float as such. And as you can see, all your outputs are floats. You've got the dot at the end of the digits or the numbers. Now, by default, this is an np64, float 64. Let's say you would want a float of 32 bits. You would have to specify. You've got float 16 as well. So you've got 16, 32, 64, and also you've got 128, which is the maximum. You do not have 256 bits. Okay? The maximum is 128. Okay. Now, this is it for matrix addition. Let's go ahead and do some matrix subtraction. Matrix subtraction. Matrix subtraction is really close, so instead of the plus, we've got a minus as such. This is your matrix. And let's say you'd want to do it the other way, which is more flexible in terms of casting. So np.subtract a, b, and let's say you would want an integer or a float, np.float. np.float 64, and there you have it. Okay, this is matrix subtraction. You've also got matrix multiplication, and this is not the usual multiplication that you know of if you've worked with linear algebra. This is pointwise multiplication. Of course, this is an error because I have to specify it as a markdown, as a comment, right? How do you do that? Well, it's as a times b as such. So as you can see, let's pick this entry, the one sitting at the second row, third column, and let's also print next to it a and b. Sorry about that, it's uppercase b. So 9 times 5 is 45. This is pointwise multiplication. And the second way of doing pointwise multiplication is using np.multiply a by b by, if you want to specify a data type, which is, let's say, a float again, 128, for no reason. Okay, there you have it. And you've got the fourth and final basic operator, which is matrix division, right? And matrix division in our case would be C is A divided by B. Now there is an error, there's a warning, runtime warning, divide by 0. So of course, you cannot just, divide by 0. So if you take a look at C, you'll have an infinity, right? Because B has a 0 right here, and an 8 right here. Okay? So this would be infinity. Python will throw a warning. Okay, so you can also divide by np.divide a, b, and you can also specify a data type. Let's say you want an int 128. I don't think there's an int 128. There's, maximum is 64. But we have an, okay, you cannot cast it, you cannot cast a float in this case to an integer. You can only cast a float of different precisions as such, which work right now. Print C, there you have it. Okay, if you want to remove C from here, you get the warning and the output. If you assign it a value, you will not see the output. You will have to print it on another line separately as such. Okay, so you can only, for division, because division, you're more expected to get, if you're working with integers, A and B, integer matrices A and B, and you perform pointwise division, right? This is pointwise. This is not the inner product division, which is an inverse times another matrix. No, this is pointwise. This is easy. This is basic. So yeah, in case you're dividing pointwise two matrices or even two numbers, the output is most probable to be in a float, right? So that's why automatically your output will be casted as a float, and you cannot cast it back as an integer. Now, if you insist on casting it as an integer using you can use np.int and choose the precision you want. Let's say int 16, run, and there you have it. You get the integer parts of your floats. So 1, 1, 1, as you can see here. 0, by default, infinity is 0, 0, 0, 0, and 0, 1, 0. Okay? You cannot cast it from the divide operation. Okay, so that's it for matrix operations. Now, let's say I'm interested in doing some matrix products or matrix vector products. Let me put this as a heading. You can also put it as a heading. This is a level 2 heading. So there you have it. So a heading is a title. If you've worked with HTML, you know that you have 6 types of headings that come in different sizes. Okay, so let's work with matrix products. Now, the first thing you want to know is the usual matrix product, which is the inner product, which is done as follows. So np.matmul, which means matrix multiplication. So this is not pointwise multiplication. No, this is the multiplication that you know in terms of matrices, the usual multiplication, which is defined as such. Sorry about that. So C is A times B as such, where, okay, so where the ijth element of C is written as such. Sum A1 to N, right? A, I, K, B, K, J, which is such, where Cij is the ijth element of C. Okay, so in other words, it is a, if you want the first element here, it's the first row of A multiplied by the first column of B, and then you add up the elements, the dot product or the inner product. So 156 times 416 is 4 plus 5 plus 36, which is 45. Okay? This is how you do it. Now, this is one type of matrix multiplication. Of course, you're going to get an error if you multiply with incompatible dimensions. So let's say you have a matrix X, which is not compatible. So let's say you have the following matrix. Which is rectangular, and I'll call it R instead of X because it's rectangular. So R looks like this. Actually, you could multiply A by R, but you cannot multiply R by A. So let me show you what I mean. Matmul, A by R works, but R by A does not work. You get an error, incompatible dimensions. On the other hand, R transpose with A should work, right? So there you have it. So this is the transpose operation, and this is how you do it, dot transpose. Good. So this is matrix multiplication, inner product multiplication, of course. Now, let's say you have two vectors. say I have the first column of A, or the first column of A as such, and lowercase b is the first column of B. As simple as that. Now, you're interested in performing a dot product between two arrays or vectors in terms of linear algebra. How do you do it? You could use matmul, of course, and do A with B. This is an error because they are both of same, incompatible dimensions. Oh, but NumPy is too smart to figure that out, so it will transpose one with respect to the other. Now, another way of doing that is using the dot, a dot product between two vectors, which is defined as the following. So if you've got two vectors as such, if you're working with in a real space, it's defined as such. It is nothing other than this equation. Okay? Now, forgive me, I am showing you how to write LaTeX. For those of you who know how to use LaTeX, this is good. This is good practice to use it in Jupyter. And for those of you who are not familiar with LaTeX but would like to learn it, this is a short overview of how you do it, how you do some basic stuff. And there you have it. Okay? This is the dot product. Okay, now let's say you want the inner product of two arrays. So np.inner or linalg, which is the linear algebra library, dot inner. I think this is deprecated. I'm not sure. Oh no, it's not. It's here. So the inner product is also 5. So those terms are, they're redundant over here. You've got dot, you've got inner, which is good because no one is going to expect you to memorize much notations or syntax. So let's say some people are familiar with inner product, some people the dot product and matrix multiplication. So you can use those three interchangeably. Okay, that's really good in my opinion. Now let's say you're working with tensors. So tensor dot A with B. We're going to get an array of this size. This is C, and C is array 146. So if I no, this is not how we do it. Nope. This tensor dot, I think it doesn't work with. So let's read about it. You can expand right here. Given two tensors, arrays of dimensions greater than or equal to 1, A, B, which are the inputs, and an array-like object containing two array objects. Got the parameters, you've got notes right here. An example is this. Okay, we have to really be careful with dimensions, right? So, tensors work in multidimensional fields. So that's a generalization of some products. Now, this is what I was talking about earlier. See how many for loops you need to compute a tensor dot product? Here you need 4 nested loops, which they're telling you a slower but equivalent way of computing the same thing is as such. So for that, we're going to have to need higher dimensions to demonstrate. Let's take the same matrices they have. So this is A and this is B. This is my A, which is, you know, a 3 by 4 by 5 matrix. 3 by 4 by 5 matrix. And this is B. And I'm interested in the tensor dot product between A and B. There's a mistake. I think I'll have to specify the third parameter, which is axis. So if you've worked with tensor dot products, you have to specify over which axis you're performing the tensor dot product. Okay? 1, 0 means the first axis, then 0, 1 is the second one. Okay? Now this is for the tensor dot product. You've also got matrix powers. So to the power, a matrix to the power something. So let me demonstrate this. np.linear algebra dot matrix power of A. If I execute it like this, there's an error, of course. If we go read about it, we have to specify to the power of what, of course. So to the power of 1 is the matrix itself. To the power 2 is, of course, np.matmul, A times A, as such, to the power 10, and so on. Okay? This is matrix exponentiation. You've also got the Kronecker product, which is defined as follows in some literature. So let's say you have a C is A. Is it O dot maybe? No, this is a Hadamard product. It's the cross one. So I think it's cross. Nope, it's not recognized. And I think it's an O times. Yep, there you go. Now this is the Kronecker product, and how you do it is as such: np.cron AB. Let's say I want to display the output. There you have it. I'm not going to say how this operates. If you're interested about Kronecker products, there's a big literature on that. So basically what it does is just throws one element from A and multiplies it with all B. So if you look at the first 3 by 3 matrix, what is this matrix? Now let's take a look at B. It is B. Now actually, in the first 3 columns, you can see B replicated all over, except the last 3 rows, which is all zeros. And why is that? Because if we take a look at A, 1 is being multiplied pointwise by all this matrix, and we throw it in the first 3 by 3 submatrix or block matrix entries of the output. Then the second submatrix is also B. The third one is all zeros because 0 was multiplied by all B pointwise. Okay? Now you see this minus 1 here. It's going to invert all those elements. So 4 becomes a minus 4 and minus 8 becomes an 8. You can see it right here. So right here. So this is basically what a Kronecker product is. Now that's it for the basic or the most known or most famous matrix products. Okay, so let's talk about matrix decompositions. So I'll use that as a heading and go. Okay, so in NumPy we've got some useful matrix decompositions. Let's start with the first one, which is Cholesky decomposition. So let me type here Cholesky decomposition, aka the following. If you have a matrix A, you can decompose it as such. Cholesky decomposition is U Hermitian or transpose in case of real numbers. and you will get the matrix U from A. So let's say you've got your A as such, right? So your Cholesky decomposition is np.inner algebra dot Cholesky with A. So your U will look like this. And to verify np.matmul A with the transpose of A. What is the error over here? No, it's U. Sorry. Transpose as such. And there you have it. Now, I know there's some, okay, so you're not getting exactly A, you're getting an approximation. There's some mathematical reasons behind that. In some cases, your Cholesky decomposition is an approximation, okay? It's not complete. It's not like exactly A. Some cases, it's an approximation. And in general, if you have complex matrices, you have a conjugate. You have to mention a conjugate right here. In general, this is the formula. So transpose conjugate is the H you see right here. Okay? Now let me give you another example where you will get exactly the solution. It's either when, let's say you have a matrix T, np.dot, and this time let's put a complex matrix. So 2j and 5 and such. So you've got this matrix and you're interested in performing the Cholesky decomposition of D. How do you do that? As we did before, linear algebra dot Cholesky of D. And then to verify, you need a matmul U with U transpose conjugate. Is this going to give me D? And as we can see, we get exactly D. Now, there is a shorthand for the transpose operator. Instead of transpose as such, you can simply go ahead and type in T, and you'll get the same thing. So if you have a matrix A, you're interested in the transpose, you can do it as such. And I always forget the S here. So in my case, I would prefer this over transpose. Okay? So this is everything about Cholesky decomposition. You also got the QR decomposition. So QR decomposition, which is a matrix is equal to Q times R, as it says, where Q is an orthogonal matrix and R is upper triangle or lower triangle. Not sure. So let's demonstrate this. A is the following matrix, and let's say you would like the QR decomposition. So here you have two outputs. In the Cholesky decomposition, you had one output. So how do we handle that? Well, np.linear algebra dot QR of A, you see two outputs right here, and they are in the form of a tuple. So the way to extract it is simply 0 would be the Q matrix, and 1 would be the R matrix, the upper triangular matrix. So let's put them as such. Q is this, and R is that. Now we have Q and R, and how do we verify that A is indeed Q times R? Well, np.matmul Q with R, and you will get exactly A. Okay? So this is A transpose A as such. There you have it. Okay? Okay, so this takes us to the next topic, which is eigenvalue decomposition. decomposition, or EVD, which is basically given a matrix A, get the eigenvectors and the eigenvalues of the matrix. Markdown. Okay, so given A, get P and D, where P is the eigenvectors, consists of the eigenvectors, and D is a diagonal matrix consisting of the eigenvalues of A. So how do you do that? Simply by running np.linearalgebra.eig of A. Now, as you can see, you have two outputs. First one is 3 elements consisting of the diagonal elements of D, and the second one is the matrix P. So you can extract those outputs as we did with QR, but we're not going to do that because it is bad practice. I just showed you one possibility, which is a easy one. The other one is more compact and faster, right? Let's say you've got a very big matrix, and this will consume some amount of time. So you don't want to do the same operation twice. You'll do it once, and you store the outputs as we're doing here. So the first output is D, and the second one is B, as simple as that. So run, your D will look like this, and your P will look like this. Now, to verify this relation, we need to multiply P by D by P minus 1, or P inverse. Notice that we have two multiplications, and that D is a matrix and not a vector. So first thing we need to do right here is convert D to a diagonal matrix, and this is achieved by np.diag, or diagonal of D. So now uppercase D looks like this. It's a diagonal matrix consisting of the eigenvalues. And now we can perform, let me just remove those. Now we could perform the multiplication we talked about. So the first multiplication is P with D, right? And the second one will be with P inverse. So how do you invert a matrix? P dot linear algebra dot inverse of P. And then np.matmul, or matrix multiplication, of P with D and with P minus 1 as such. So let's run this, and there you can see we have matrix A. Now it's not looking really nice because you have those floating points right here. Now let's extract the real part, because the imaginary part is all zeros, right? So run, there you have it, 1, 1, 0, because 10 to the power minus 16, which is 0, and 5, 8, minus 1, and 6, 9, 6. And this is it for eigenvalues, or eigenvalue decomposition. Let's say you're just interested in the eigenvalues. You don't care about the eigenvectors. You can do np.linearalgebra.eigenvals as such of A. And there you have the eigenvalues, okay? Now you've got one more decomposition, which is the singular value decomposition. Singular value decomposition, or SVD, which is simply given a rectangular matrix or a square matrix. You can decompose it as follows. USV transpose. I keep doing the same mistake. This should be a markdown and not code. So there we have it. And now given A, we should extract U, S, and V transpose. So this is achieved as following. np.linearalgebra.svd, right, of A. And we have three outputs. They are U, the vector corresponding to us, and V transpose. So as we did before, we're going to extract them using tuples. U, S, V is this, and then you need to convert S to a suitable diagonal matrix to multiply US with V transpose to verify that this relation is true, to convince yourself. Okay? Now this is it for matrix decompositions. Let's talk about some norms, or functions that take matrices as input and returns a number as an output. So I'll call them matrix norms as such. Now the first one is the usual matrix norm, which is np.linearalgebra.norm of A, which is the Frobenius or L2 norm of a matrix A. Okay? The second one, which is really useful, is the conditional number of a matrix A. It tells you how close to singularity it is. So this is A. Let's check B as well. So B is really close to singularity, which means its smallest eigenvalue is in absolute value is close to 0. It's closer to 0 than A than that of A. Okay. You've also got the determinant of a matrix. Linear algebra.det of A is 21 for A. Let's check that of B, 336. Okay. And you've got also the matrix rank, the rank of the matrix. So matrix rank of A is 3. That of B is also 3. We've got R, it's 3. U, and so on. We've all got full rank matrices. Next up is the trace of a matrix. np.linearalgebra.trace. It's found in the np library, I guess, not in the, yeah, it's the trace. Trace of the matrix is the sum of the diagonal elements. Let's input R. Let's input small d, and there's an error. It has to be square, or at least 2 dimensions. Let's create a random matrix just to verify. A random square matrix, no, a random rectangular matrix. So R looks like this, and let's take the trace of R, and it just sums up this, this, and this. Okay. Now usually the trace of a rectangular matrix I think is not defined. It's not properly defined, but in NumPy they define it by default to be the sum of diagonal entries. Okay, now let's talk about solving equations. Solving equations. Markdown, no, I want it to be a header. We get it. We want this to be a header. And let's solve, let's say I have the following system of equations. Ax is equal to b. You have a, you have b, and you would like to find x. So this is your a, for example, and your b is the following. Dot random 3 by 1, and it looks like this. Okay. Now, of course, you have multiple ways of doing that. You could choose to say x is, so let's say x1 is the first solution, or the first way of finding the solution. It is np.linear algebra dot the inverse of a times b. So we need the matrix multiplication here. So run, and let's check what x1 is. Looks like this. The second way is to use the NumPy solve function. A, B. And let's check what x2 is. There we have it. And you've also got other types of inverses as well, because inverses is solving the following. You're finding a matrix X to solve the following particular system, right? Let me change it back. So we talked about np.linear_algebra.inverse. Let's say your matrix is not invertible. Let me give you a matrix that is not invertible. np.array. So 1, 2, and 2, 4. This matrix, for example, is not invertible. And to check np.linear_algebra.invert as, you get an error, singular matrix. So instead, you have something else called the pseudo-inverse or the Moore-Penrose inverse. It's a semi-inverse. It's an approximation of an inverse such that the following multiplication is close to identity. Okay? This is the best you can do in this particular matrix. Okay, so we've covered almost everything related to linear algebra and NumPy. These are the basic stuff and the most important stuff you need. So we talked about matrix addition, subtraction, multiplication and division. We also covered matrix products right here, inner products, dot products, tensor products, right? We talked about matrix exponentiation, Kronecker products. We also talked about matrix decompositions, such as Cholesky decomposition, the QR decomposition, the EigenValue decomposition, and the SingularValue decomposition. Other stuff we covered is related to matrix norms, such as the L2 norm, the conditional of a matrix, the condition number, the determinant, rank, and trace of a matrix. We also talked about how to solve system and linear equations using either inverses or the solve function within the NumPy linear algebra library. And we also talked about the pseudo-inverse in case of singular matrices. Okay? In other videos, I'll cover other sub-modules of the NumPy library, such as statistics and finance and so on. I'll see you in later lectures. And thank you for watching.